Okay, we've talked about linear stuff. Now let's talk about moving in circles. So in order to talk about moving in circles, we have to talk about centripetal acceleration. In order to talk about that, we have to talk about circular motion. And in reality, we're going to talk about uniform circular motion. Uniform circular motion means you're going around in a circle at a constant speed. Constant speed circle. Examples of uniform circular motion, your tire going around in circles when you're moving at the same speed would be uniform circular motion, something like that. So let's draw a dude, and we're gonna have that dude hooked on to, I don't know, little sister. I used to do this when I was a kid. And what we're going to do is whirl this. Now this is three-dimensional, so it's a little hard to draw. We're gonna whirl my sister around in a circle, and I used to pick it up. This was for fun. Now this wasn't designed to hurt her, and I'd pick her up and I'd move her around in circles the whole time. And what would happen was her velocity is actually tangent to the circle. If I let go of her, that's the way she's going. So her velocity would be tangent to the circle, but her acceleration is this direction, and her acceleration is what actually turns her. Anytime velocity and acceleration are perpendicular to each other, you're going to move in a circle. So in other words, if I have an object that's wanting to accelerate in that direction, wanting to go in that direction, and I apply an acceleration in this direction, it's going to move in a circle. Even if it's just a part of a circle, it's going to move in a circle. So that's what we're talking about with centripetal acceleration. Now let's make sure we understand that when objects move in a circle, well, we know speed is equal to distance over time. Well, if we're talking about something moving in a circle, like for example my sister, the distance around the circle, circumference. And then we know that circumference is 2 pi times r divided by t. That's the speed at which something will travel around a circle. This is oftentimes called the period. It's the time for one revolution. And then of course 2 pi r, so it would depend upon the radius. How fast the object would be moving would depend on the radius. For track athletes, for example, a discus thrower with long arms has a built-in advantage. Since they have a longer arm, they can make the discus move at a faster speed. You get it to a faster speed, more kinetic energy, it can potentially go farther. So we'll look at that. Okay, now, so that's the way we calculate distance if we know the radius of the circle and the time at which it takes to go around. Now the other thing we're going to calculate is centripetal acceleration. Now there's a derivation of this that's out there, and feel free to look it up. I'm more concerned with using it than deriving it. It says centripetal acceleration is equal to v squared divided by r. So in other words, it's speed squared divided by radius. So it's the speed at which you're moving. Now, here's the thing that can happen with this. By the way, let's take a look at the units, because you know I love units. So let's take a look at that. If I have speed squared, well, speed is meters over seconds squared divided by radius, which is going to be in meters. So I'm going to get meters squared over seconds squared divided by meters. When I multiply by 1 over meters to get rid of that, one of your meters cancel out. I'm left with meters per second squared. That's an acceleration unit. Oh, life's wonderful. Now, a couple things to understand. First of all, if A and V are perpendicular, you're moving in a circle. Moving in circle. Or at least part of a circle. So that's important. It is related to the speed. This is the one case where speed can be constant and you accelerate. Why are you accelerating? Now, the reason you accelerate goes back to our initial definition of acceleration. It said anytime you're changing velocity. In this case, what you're doing is changing direction. Since you're changing direction, you are accelerating. So let's take a look at, see if we can apply that to some example type stuff. Let's say we have this is a top view. And let's say we're whirling a hammer. In track, hammer's a sport. They don't throw it in high school because it's a little dangerous. But this is a top view of a hammer. A hammer is essentially a shot put on the end of a cable, and they twirl it around in circles. So what's going to happen if I ask you to draw the V and A vectors? Could you? Think about that. Could you draw it? You're going to have to. So I'm going to require you to do it. Well, velocity is tangent to the circle, wherever the object is at the time being. It has to be. No choice about that. And then acceleration is towards the center. Centripetal actually means center seeking. That's what that term means. So when you see that. So therefore the velocity vector would be right there. The acceleration vector would be right there. If I do it at this point over here, the velocity is there. The acceleration is towards the center. The acceleration is always going to be towards the center. So you need to understand direction with it. And we'll play with the numbers a little more when we talk about centripetal force, which will be the next unit. And then we'll go and we'll look at how we can apply that to the real world. Key thing to understand is velocity and acceleration are perpendicular to each other when you're moving in a circle. The velocity is tangent, the acceleration is towards the center. The acceleration, centripetal acceleration, is calculated by v squared over r. The speed around the circle, which would be the tangential speed, is actually 2 pi r divided by the time for one revolution. So we'll apply those equations to various and sundry ways that I can come up to make you understand this stuff. Have fun.